Welcome to this session. I'm Dr. Sreekanth, Professor, Department of Data Science, Institute of Aeronautical Engineering College. And today we are going to discuss the groups, properties, and related problems. Now, what is a group? In the last session, we discussed what is a group. So here, a monoid which is going to be satisfies the last condition, which is going to be satisfies this condition, then such monoid is called a group, or a semi-group which is satisfying these two conditions, then it is also known as a group. So in general, any G is a non-empty set and a star is any binary operation defined on G, then G is called a group under the operation whenever these four axioms are satisfied. One is A star B. This is small a star B belongs to Z. This is true for all A comma B belongs to Z. And this is a closure, that is a star is closed under binary operation star, and star is associative. Then the associative principle is A star B star C is equals to just this is satisfies. Then every non-empty set will have an identity element. So E such that A star E star A is equals to A. This is true for all values of A belongs to G. And next, every element will have a inverse. Exist is every element will have a inverse in such a way that suppose A is we are going to consider a value, then A dash with the property A star A dash or A star A dash is equals to E. That means whenever if you are going to multiply with its inverse, then we are going to get the identity element. So whenever any non-empty set under the binary operation star which satisfies these four conditions, then we are saying it is a group. Now let us a group, G is a group and under the binary operation star, then if it is satisfies the commutative property, that is A star B is equals to B star A, then we can say that the group is an abelian group. The group is an abelian group. A group is said to be a finite group if G is finite. Otherwise, we can call it as a infinite group. Now, we are going to discuss some of the problems, examples on this. So, suppose Z is a integers and under the binary operation plus, then automatically, if I am going to consider a integer set, so whatever which is going to be, if I am going to add two integers, is resulting is also integer, and integers also satisfying associative property, and next integer, the additive identity is 0, which is there in the integer set, and next any element A, if I am taking an integer, then definitely the inverse is minus A will be there in the integer set. So we can say that Z, the integer under the binary operation plus is a group, So here it is also an abelian group. So because A plus B is equals to B plus A. So this group is, which is a infinite because the integer set is infinite. So we can say that it is a infinite group. It is a infinite group. So this is the way that we are going to verify whether the integer set is a group or not. In the same way, suppose if I am going to consider the binary operation is negative, then it is not a group. It is not a group. Suppose if I am considering which is not satisfying associative property, which is not satisfies associative property. So which is not a semi-group as well as it is not a group. So now the other one is the usual multiplication. So Z. So here if I am considering Z is an integer set, then the binary operation is then we are going to consider it as a star is the binary operation. Then if I am going to consider this, then it is not a group, because if I am taking one integer and under the binary operation multiplication, the inverse of 2 is 1 by 2, because this is the product identity is nothing but 1. Multiplication identity is 1. So 1 is there in the integer set, but any element if I am considering, then its inverse does not exist. Its inverse does not exist in Z. So we can say that Z comma into is not a group, even though it is a monoid, but it is a monoid, and it is automatically, whenever it is a monoid, then automatically it is a associative semi-group will be there already. Then it is not only not a group, but it is a monoid. And the next another one is another example. Let W4 is 1 comma minus 1, I comma minus I. This is wrong. I comma minus I is the set of 4 roots of unity. The operation table, the multiplication operation table is given in this table. Now we have to verify. So W4 comma star is a group or not. That we have to verify. So here these are the elements will be there which are members in W4, and here are the elements, and here are the elements. So once if I am going to multiply 1 into 1 is 1, 1 into minus 1 is minus 1, 1 into I is I, 1 into minus I is I. Next minus 1 into 1 is 1, minus 1 into minus 1, 1, like that it will be there. Observe here, whatever the things will be there, whatever the elements we are getting, all the elements members in W4. All the members are elements in W4. So we can say that it is closed under the operation into, under the binary operation into. And now associativeness, while proving associativeness, any 3 elements if I am going to consider, let us say 1 minus 1 or 1 minus 1 I if I am considering, then 1 into minus 1 into I, and I am going to verify whether this is equivalent or not. So which is satisfying the associative condition or not. So for that 1 into minus 1 into I, it is 1, and then 1 into minus 1, it is minus 1 into I. Now observe this. See here, 1 into minus 1, 1 into minus 1. Now it is, see it is 1 minus 1 into I, minus 1 into I. So it is a minus I, So this is a plus I. Then it will become plus I. And here it will be, then it is, this is what I am saying, I am taking 3 elements. Let us say this is I. And then this will become minus I. This becomes minus I. And here it is minus I. And here it is minus I. So which is satisfying the associative property. In any 3 numbers you are going to consider from W4, I am taking minus 1 I minus I. If I am taking, then minus 1 into I into and minus I. If I am considering in this way, minus 1 into I and next into minus I. So this is minus 1 and I into minus I square minus I square, it will be 1. Then it is minus I into minus I. So this is minus 1 minus I square. So I square is equals to minus 1. So it will become minus 1 once again. This is plus I square. So this will become minus 1. So which is satisfying the associative condition. And now what is the identity element? First one, it is closed and as well as it is a associative. Now what is the identity element? So here the binary operation is a multiplication. So multiplication identity is 1. multiplication identity is 1 is there in W4. So obviously the set W4 comma into is having identity element. Now inverse, what is, let us consider if I am taking one element, let us say I. So I, if I am considering where it is minus, where it is equals to 1. So I inverse is equals to minus I. So the product, when it will give 1, the corresponding element is the inverse of that. So if I am considering I into minus I is equals to 1. So I inverse is minus I. And similarly, minus I inverse is I. Minus I inverse is I. Similarly, 1 inverse is 1. 1 inverse is 1. Similarly, minus 1 inverse is minus 1. So if I consider any element from this set, and each and every element will have a inverse, so we can say that W4 comma multiplication is a group, and G is a finite, so we can say that it is a finite group, and it is having only 4 elements, so we can say that the group of a finite order, of a finite group of order is 4. Of order is 4. This group is a finite group, and we can say that the order of the finite group is 4. Nothing but the number of elements which are existing here in that group. Order is nothing but number of elements exist in the group. Now, some of the properties that we are going to consider. In any group, in any first theorem, in any group, there exists only one identity element. Only one identity element. Okay. So, that means identity elements will not be more than 1. Suppose if I am considering last problem, see here W4 into, so it is a group, whenever it is a group under binary operation multiplication, so it is having only one identity element that is equals to minus 1, that is equals to plus 1, sorry. So that means it does not have more than one identity element, that we are going to prove here. So let us assume that, I am going to assume in a contradiction manner that it has 2 identity elements. It has 2 identity elements in a group. Let those 2 identity elements are E1 and E2. E1 and E2. First, let us consider, I am just taking E1 is an identity element. E1 is an identity element. Now, of course, it is a member in Z. I am considering any one element, A belongs to Z. So now what I am going to take A, and next E1 is equals to E1 A is equals to A. Because I took just A, E1 is the identity element. In the place of A, I am just taking another element, let it be E2. Let it be E2. In the place of A, E2 is also a member. E2 is also a member. So, I am going to consider another one. So, here, instead of A, I am just taking E2, E1. And next, E2, E1. Sorry, this is, I am going to write it as E1, A. So, this I am going to write it as E1, E2. So already what we are going to say that if E2 is the identity element, then this will become E1. If I am taking E2 is the identity element, if E1 is the identity element, then this will become E2. E2, E1 is equals to E1, E2. What I am going to get? See here, if I am taking E1 is the identity element, E2 is the identity element, then I am going to get the entire thing is equals to E1. If I am taking E1 is the identity element, I am going to get this as E2. So what I am going to get, I am just combining E1 is equals to E2, then it is equals to this one. So I can say that E1 is equals to E2. So even though if we are going to assume that it is having more than one identity element, but those identity elements are equal to each other. Okay. Now, let us go for the other theorem. In a group, every element will have only one inverse. So last problem what we discussed, if I am taking I inverse is equals to minus I, and there is no other inverse of that element. If inverses exist for any element, that should be unique. That should be unique. So here also, let us assume that it is having two inverses. A is having two inverses. Let us say A dash and A double dash. Element A is having two inverses. One is A dash and another one is A double dash. Suppose A dash is one inverse of A, then I am going to write A dash is equals to A dash A is equals to E. Is equals to E. Suppose if I am taking, this is the identity element, then A inverse, if I am taking A double dash is equals to A double dash A is equals to A, and this is E identity element. This is the identity element. So if this is the inverse and this is the inverse, then this is going to be true. This is going to be true. Now let us go for, I am just taking A dash is equals to, I am going to write A dash into E. E is the identity element. If A dash is an element, belongs to G, so A dash I am going to write it as A dash into E. So then it is A dash into E is, I am going to write like this. I am going to write like this. So A double dash, A double dash, I am going to write. Then here it is a group, so it satisfies associative law. So it can be written as like this because it satisfies associative condition. Now this will become A dash is the inverse of A. So this is E by this condition, and then it is A double dash. So E is the identity element. Identity element is multiplied with any element, then I am going to get that element itself. So I can say that A dash is equals to A double dash. A dash is equals to A double dash. So from this we can say that, even though A will have more than one inverse, A dash and A double dash, but they are equal to each other. So we can say that any inverses exist for any element, then those values are equal to each other. Then the another one. For any elements A, B in a group, we have A inverse whole inverse is equals to A, and AB whole inverse is equals to B inverse A inverse. Now let us assume that when we can say that one is inverse of the other, whenever if you are going to consider in a function or anywhere, when we are going to get, suppose if C is the inverse of A, then I am going to get AC is equals to CA is equals to the identity element. So identity element. So what is that identity element? Here I am taking it as E. So then we can say that A is the inverse of C. Or we can take it as A is equals to A, we can write it as C inverse. So both are inverses of each other. Now I am going to replace C with A inverse. I am going to replace C with A inverse. So A inverse is equals to A inverse. A is equals to E. So what is A is the C inverse is equals to A. So what I am doing in the place of C? We have A inverse whole inverse. A is equals to A inverse. I am just replacing C with A. C with A inverse. And next, another one. In the same way, I am going to prove this. The second concept. So here also, what we are going to see that then the same logic that we are going to use for this to solve this. So here, just we are going to say that, just we are going to take it as AB, then B inverse, A inverse, B inverse, A inverse is equals to, and next B inverse, A inverse into AB is equals to E. This we have to prove. This we have to prove. So for that, we are just taking AB, B inverse, A inverse. I am just taking this, and this is A, B, B inverse, and A inverse. So here, because it is a group, so it satisfies associative law. So I am going to write like this. So this is A, E, A inverse. E is the identity element. If I am multiplying with A, so we are going to get A inverse, which is equals to E. And in the same way, B inverse, A inverse, and AB is equals to B inverse, A inverse, A, next B. So it is B inverse, EB. So it is B inverse, B. So this is E. So what I am going to say that this is the inverse of this. So earlier C is going to be replaced with AB. C is going to be replaced with AB. So I am going to write it as AB inverse is equals to B inverse, A inverse. B inverse, A inverse. So this is the second one. Now the another simple results will be there. That means G is be a group, and A comma B comma X be any elements of G, then this condition is satisfied as well as this condition is satisfied. That means this is nothing but the left cancellation law is applied and the right cancellation law is true. That means in a group, left and right cancellation laws are holds. So let us consider, I am just taking the given thing will be there. Then X is an element in the group, so X inverse is going to be exist. Every element will have its inverse, so X inverse is going to be exist. So which is also a member in G. So now we are going to pre-multiply the X inverse on both sides. So I am going to get like this. And once associativeness is going to be applied, so X inverse X into A, X inverse X into B. So it is EA, this is E, and this is also E. So EA is equals to EB. Then EA is nothing but A, because E is the identity element. EB is equal to B. So we can say that A is equal to B. A is equal to B, which is nothing but the left cancellation law. What is that left cancellation law? X is equals to XB means left side whatever the element will be there, that is going to be cancelled. Then this will become A is equal to B. So this is the left cancellation law. And now the right cancellation law. The second one is the right cancellation law. So right cancellation law, just we are going to take and we are going to apply X inverse. Post multiplication we are going to do that X inverse. So AX is equals to BX. So which implies I am going to apply the post multiplication with X inverse. So BX and X inverse. So which is A, X inverse, and next B, X inverse. So which is equals to AE is equals to BE. So which is A, which is equals to B. So this is also the right cancellation law. The right cancellation law means whatever the element will be there common, that element's right side we are going to simplify. So this is the right cancellation law. We applied right cancellation law and then we are going to get the final result. So in any group, if you are going to consider, the left as well as the right cancellation laws are going to be held in a group. Now the another theorem. Let G be a group and A comma B belongs to G. Then AX is equals to B has a unique solution, and y a equal to b has a unique solution. So here x, let us consider, we are just taking x is equals to a inverse b. When we say that anything is going to be a solution of an equation that is going to be satisfies the equation, then we can say that that is the solution of the given equation. So the equation ax is equals to b has a unique solution means any expression, if I am considering for x, if it satisfies the equation, then we can say that if satisfies that equation, then we can say that that value is the solution of that equation. Any expression, if you are going to substitute an equation, the equation is satisfied, then that is the solution. So here the same concept, we are just taking a inverse b. I am just substituting ax equal to b in that. I am going to ax is equals to, I am just replacing x place as a inverse b, and we have to verify. So ax is equals to, x is replaced with this. So once again applying associative law, so a inverse b. So a inverse is equals to e. So eb is equals to e. eb is equals to b. So we can say that, so right hand side, whatever the right hand side value will be there, that is going to be there. So the expression x is equals to a inverse b satisfies the equation ax is equals to b. So I am saying that it is a solution. Now we have to prove that whether it is a unique solution or not. We have to prove it is a unique solution. Let us take that whatever the thing will be there, then that is going to be x1 and x2 are, see here x1 and x2 are two different solutions of the equation ax is equal to b. So obviously x1 and x2 are two different solutions will be there, then automatically that equation will be satisfied with x1 and x2. So ax1 is equals to b, ax2 is equals to b. So b is replaced with ax2, any one equation if you are going to consider. So here ax1 is equals to b is replaced with the other one, so ax2. In the above equation, in the above theorem, the left cancellation law is going to be true, is holds for a group. So apply left cancellation law. So I am going to get x1 is equals to x2. x1 is equals to x2. So x1 is equals to x2. That means if I am going to assume that the solutions are more than one, even though they are different, if I am taking, then those different solutions are also same. So that is the way that we are going to apply. That is the way that we are going to prove for the uniqueness. And similarly, for the next one also, we have to prove in the same manner. So here it is not ya, it is ax. This is I am taking ax, xa. So xa is equals to b. So for this, I am going to prove this. This is the solution. For that, once again, x is nothing but a inverse b, and next a. So this we have to consider. Then see, this is so xa is equals to xa, a inverse b is equals to xa. So it is a inverse b is equals to, so here I am just taking this as, then a inverse ba I am just taking, and next by applying the associativeness, and after that we are going to take it as ab is equals to, then so this is I think so xa is equals to b. So then I am just taking a inverse ab, then this is a inverse a and b, so which is equals to eb, then it is b. So in that way we are going to prove this. The second one is also in the same way, and uniqueness is also going to be same, in the same way we are going to prove. And now the next one is determine the problems on a group. Determine whether the set of integers with the binary operation is a group. If it is a group, determine whether it is a Boolean group or not. So Z is an integer set and star is ordinary multiplication. So I am just taking Z is this, and next we have to verify. Whether it is a binary, it is a group or not. It is a group or not. So for that, once see here any two elements if I am going to consider. So the product of any integers is again integer, so it is closed. And next the associativeness if I am going to take, then the associativeness is also going to be true. And then the multiplication identity is equal to 1. So 1 is also there, and so it is a monoid. But the element if I am considering 2, its inverse under multiplication is 1 by 2, and this 1 by 2 does not belongs to Z. So the inverse is not there, so it is not a group. And the second one, the binary operation is a subtraction. We already discussed subtraction is minus, so which is not going to be associative. So in the semi group, we have discussed those things, same one. So the subtraction is not a associative, so it is not group even though it is not a semi group. So all rational numbers. Now Q is the set of all rational numbers. And now the third one is set of all rational numbers, and the binary operation is addition. So here the binary operation is addition if I am going to consider. So now we have to verify. See, any rational number if I am going to consider, then it is going to be the addition of two rational numbers, again a rational number. So it is closed, as well as the binary associativeness is obvious. So it is also the three elements if I am going to consider in any order. If you are going to adding, then the result will be the same. So it is associative, it satisfies. And next it is having the identity, also it is having the identity element, that is 0. So then this is additive identity element is also a member. So it is having the additive identity. Then for each and every element if I am considering, suppose if I am taking 3 by 7, if I am taking one element, a rational number, then its inverse is under addition. It is a minus 3 by 7 is also a member. So it is a group. And next, in addition, it is a group. Now we have to verify whether it is an abelian group or not. So for that, A plus B is equals to B plus A. So it satisfies commutative law. In any order you are going to consider a rational number. So it is obviously, it is an abelian group also. Then the another one is Q is the set of all rational number. And next, the multiplication. The binary operation is a multiplication. So now the binary operation is multiplication. So now we have to verify whether it is a group or not. Same thing here, it is a addition, here it is a multiplication. So here it is also a group. Let us consider the identity, multiplication identity will be 1 is the member, and any element, any rational number if I am considering, and its inverse is also a member, its inverse is also a rational number. So we can say that it is satisfying inverse also for each and every element is going to be exist. And next another one is the identity element is also exist. And next multiplication associative also is true. So in all the aspects it is a group, and at the same time it is also satisfying the commutative law. So it is also known as a abelian group. Now let us go for the other one. Let G is equals to one set is there, and star is an abelian group defined on the Z, and now we have to verify whether G is a abelian group or not. Is a abelian group or not. So we are going to see how the binary operation is related. How the binary operation is related. That we are going to mention. That we are going to represent in a table. And we have to verify whether it is a group or not. So here, observe all the elements are members in this. So obviously it is closed. So the resulting, these are the elements of the set, and these are the elements from the same, from the set G. So this is the under the binary operation, whatever the elements that we are going to obtain, those elements are members in G. So we can say that it is closed. G is closed under binary operation star. And now the associativeness, I am going to take in this way, and I am going to verify what is the value of this, So A star B, and let us say A star D. I am going to verify star C. Let us take the other one. So it is A star D star C. So this I am going to consider A star B. A star B is equals to A star D is equals to D star C. And next A star D star C. D star C is equals to B. Next D star C. D star C is equals to B. Then A star B is equals to B. Both are same. So this is the other way that we are going to take ABCs. I am going to consider here. ABCs also we are going to verify. A star B. What is A star B? A star B is B. So now this is the result of this is this. And C will be there as usual. B star C. B star C is equals to D. And similarly the next one, if I am going to consider, I am going to get like this. So in any order, if I am going to consider three elements, then it satisfies associativeness, associative law. Then what is the identity element? Now let us go for the identity element. A star B. What I am going to get? B. And B star A. What I am going to get? A. See here. A star B is equals to B star A is equals to what I am going to get? A star B. B star A is equals to B. That means what is A as an identity element? Let us go for the other one. C star A and A star C. What about this? C star A. C star A is C and A star C is also C. And now take the other element. D star A. Then A star D. What about DA? DA is equals to D. AD is also D. So here, which element is an identity element? So here A is acting as an identity element. That means if you are going to multiply, if you are going to apply any binary star operation on A, we are going to get the same element. So A is the identity element. So identity element is A. So once if you are going to get the identity element as A, then we have to verify the inverse. So let us go for B inverse. So B inverse, while checking B inverse, you have to go through in that row where you are going to get the identity element. You are going to find out what is the inverse of B. So in the B row, you just go through in the same way where you are going to get the identity element. Identity element is here. So B inverse is D. So inverse of B is D. Then what about A inverse? A inverse is A itself. Identity element inverse is A itself. Next, what about C inverse is C inverse is where I am going to get A. So here, so C inverse is C. And what about D inverse is? D inverse is where I am going to get A. So D inverse is B. D inverse is B. So each and every element will have inverse. So I can say that G comma star is a group. G comma star is a group. Now we have to verify whether it is an abelian group or not. Whether it is an abelian group or not. So for that we have to verify. A star B is equals to B star A. So already we calculated all the things. So let us say C star D is equals to D star C. What about, we have to verify. C star D is what? B. And next D star C is B. D star B is C. So, okay, if I am going to multiply with identity element, the binary operation, we can get the same element, but other than that also I am going, both are satisfying the commutative law. So we can say that it is an abelian group. Now, the G is A, B, C, D, and a star is a binary operation, and which is defined. The elements are represented in the table. So, which is a group, which is an abelian group. So with this, in the next session, we are going to solve some more problems on this group. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.